All right, lesson 2.9. So as we begin here, the second half of unit 2, we're going to learn about logarithms. Logarithms. A logarithm is the inverse to an exponential expression. So the reason we cover logs while we cover exponentials is they are inverses of one another. Remember, inverse, when I say inverse, what is it that I want you to think of? I'll say one word, but it's actually one word followed by two variables. What's the one word I want you to think of when I say inverse? Switch is the word, and the two variables would be x and y. Very good. These two are how, without a calculator, excuse me, how you'll solve a logarithm is how you would solve an exponential without a calculator. All right. We're also going to learn about graphing on a logarithmically scaled vertical axis. I'm pretty sure that none of you have seen that before. It's a little neat feature, and we're going to see that as we go on. So let's begin here. About inverse operations. Everything in math has its opposites. And how you solve for algebra is you apply an opposite. So, for example, if you had x plus 3 equals 7, you might know the answer right off the top of your head. What's the answer going to be here? 4. Well, how do you actually solve that? You would subtract 3 from both sides. And so, though we had x plus 3, you would subtract 3 from both sides of the equation to get an answer. The reason we would do that is because adding 3 and subtracting 3, those are inverse operations. They cancel out. And what are you left with on the left side of your equation? Just an x. You'd be left with x equals 4. And so here with multiplication, what's the inverse multiplication? Division. And so in this case, you would divide both sides by 3. And if you divide both sides by 3, again, you could say those simplify out, they cancel each other out. Inverses cancel each other out, they simplify out of there, and you would get the answer of 7/3 here. Now, what about a cube? If you were cubing something, what's the opposite of cubing something? Here's square root. That's close. It's not. It is a root, but it's not a square root. That's the opposite of it's a cube root. That's what you'd call it. So we would apply a cube root. Again, that would be the inverse operation. And finally, we're going to make our way to exponentiation, which is a fancy way of saying an exponential equation. So here we have 3 raised to the power equals x. 3 to some power equals 7. I don't know if I said 7 the first time. I think I misspoke, but 3 to some power x equals 7. How would you solve that? Well, the opposite of an exponential or an exponentiation is a logarithm. And so what we're going to learn today is that you will apply a log with a base, which I'm always going to do. You don't have to do it this way, but I'm going to do it the easiest way, where the base of the log is the same as the base here. So it's going to be 3. That's the base. It goes down low. And then this normal 3 to the power of x. And this will equal over here log base 3 of 7. That's the way we're going to write this out. And what you're going to learn is that if you have a log with a base that's the same as the value here, those cancel each other out and they become a 1. We're also going to learn a property that anything that's a power can multiply times the logarithm. That mathematically, a power on this value here, the power on this value here, is the same thing mathematically as multiplying the logarithm outright. And so we're going to learn that that would be an inverse of each other. The log base 3 of 3 will cancel each other out, and you're going to be left with just 1x, or just x in this case. You don't have to say 1x, you could just say x. And so x would equal the log base 3 of 7. We would type that in the calculator to get an exact value, that one in particular. So anyways, what's the point? The point is everything in math has its opposite. It has its inverse. What's the opposite? What's the inverse of an exponential function? A logarithmic function, that's right, a log. Okay, so now just as we can write rational numbers in decimal form and fraction form, so like 1.5 is the same thing as 1/2, we can also write equations in exponential or logarithmic form. So you can write them in both forms and they're still mathematically equal. Because they're opposites, you can write it in either form and they're still equal. Okay, so over here, if you have a base raised to the power of a equals c, that's the same thing as log base b of c equals a. I love what Dr. Milana calls this. Dr. Milana calls this going around the world. Go around the world. And I love that phrase because it makes a lot of sense to students when they start looking at this. What you do is if you start with the B, you don't go in order B to A to C. What he says is you go around the world, and it really doesn't matter which way you go around. I'm going to go around this way. It becomes the base. Instead of being raised to A, it's going to be a log of the base raised to a C is going to equal the A. So look over here. You see it's log. What comes first? The base. You always start with the base, but is it raised to the A? What's it raised to right here? C. Yeah, the base gets raised to C, and that's going to equal A. That's how it's going to work. And so Dr. Milana calls it going around the world. I like that. It makes sense. That's how it's always going to mathematically play out. Okay? With that, I have one more slide here of how some notation deals. First notation is what we call a common logarithm. It's a log with a base of 10. If you have a log with a base of 10, you don't actually have to write the 10. Let me give you some examples what I'm talking about. If I have x to the first, do I have to write x to the first? What's another way you could rewrite that? X. And that's what we would say is x is the same thing as x to the first. I'll go one further. What if I had 1x? Do I have to write it as 1x? How could I write that? X. This is just examples of what is happening down below. So just get your mind in there. Okay, what if I had 1x to the first? What's another way I could rewrite that? X. Just x. X is equal to all those. Okay, so we write the left form, even though it's true that the right form is also true. We write it just as the left form. Okay, come down here. I'll give you one more. What is x divided by 1? X. Do you have to ever write x divided by 1? No, you can take that away. Okay, that was one more. All right, so honestly, I should probably put these all together. Let me go in order here. Whoops. Let me put this in order one more time. Come on now. There we go. Okay, all these three things you could say are equal to one another, and I'm going to put this as being divided by 1. Okay, so now come over here. You see how this says log base 10 of 3? You will not ever, ever, ever on an AP exam or anything like that, if you have a base of 10, you will not see the 10 given. It's just going to be log of 3 like that. Okay, that's the only way you're going to ever see it. One more is called a natural log. So that's called the common log. Common log's when the base is 10. One more is a natural log. That's when we have a log with a base of e over here. Okay, check this out. Log with the base of e. If you have a log with the base of e, they're not going to keep this as log base e. They're going to write it as this ln. It's unfortunate. It stands for natural logarithm. What's unfortunate is it wasn't an English-speaking person that came up with the natural log. It was Latin. And in Latin, they called it, I think it's logarithmic natural. That's how they have it written, which would mean L comes first. But in English, we don't say logarithmic natural. We say natural log. It's unfortunate. But if it was an English person, they probably would write NL. But it wasn't an English person. So just note this. Does this say, you need to all see this right now. I'm telling you, very common misconception. Does this say NL? Different question. Does it say IN? A lot of students think that means like I'm inside a building, I'm inside a fort, I'm inside a car, I'm inside a vehicle. That does not say IN. What two letters are those? LN. What does the L stand for? Log. What does N stand for? Natural. And that just means the base is E. So those are the two ways you will not see on the AP exam log with the base of E. If it was going to be log with the base of E, they will write ln, and a lot of students think it's in. Because of that, I'm going to write with swoopy L's. You'll see what I mean. Every time I write a log, I'm going to use a swoopy L just because I want students to know it's an L and not an I. Finally, log base 10 of 3, you won't see log 10. What will you see instead? Log. So check it out. If you only see the word log, what's the base? 10. If you see what looks like in, but it's actually ln, what's the base? With an E. The base is an E. Okay, with that, I think we're ready to get started. So it says convert the following equations from exponential to logarithmic, or you could just say log as I've been calling it. Log form and simplify. It is mathematically acceptable just to say log rather than logarithmic. Okay, first what I'm going to do is a shortcut. On the side, I'm just going to do the shortcut. I'm going to say go around the world model. But then I'm going to show you the algebra on the side because I realized last year when I started showing the algebra, it clicked in some students' head better. So I'm going to show you the shortcut first because some people are going to understand the shortcut and it's just quicker. So going around the world, what form is this in right now? Exponential form or is it logarithmic form? Exponential. So if you're switching to logarithmic, you always write the word log first. Log. And then you start with the base. Out of these values, which one's the base? 3. So we're beginning with the 3. The 3, with logs, you put the base down low. Now, if I'm going around the world, what value do I go to next? You go to 9. So it's going to be 3 raised to a 9. And then when you come back across the world, that's when you hit the equal sign. Equals x. Make sense? Now that we're going to learn is actually the value 2. So I'm just going to put 2 equals x underneath. That is 2. And you can check it over here. 3 to what power is 9? 2. 3 squared is 9. Would y'all agree with that? 3 squared is 9. Okay, this part we could type in the calculator, which will come up later, but we're not there. I'm just going to put 2. Okay, so now let me show you the true algebra. Here's how the true algebra would look. Like if you were ever seeing a math problem where it's like, hey, pick out which step that the person did wrong. If it's one of those type questions, here's what it would look like. The first step you would do is you'd say, hey, I need to apply a log. And so whatever you do on one side of the equation, you have to do it on the other side. You agree with that? Is that how it works in math? So what you would do is you do log on both sides of the equation. And then you can pick, mathematically, it's true, you can pick any base you want. I always choose whatever base is given to me. What was our base given to us? 3x or 9? 3. 3 is the base. So I would do log base 3ing both sides. Then you'd have 3 to the x and then a 9 over here. Everybody tracking with that? Whenever you have log base 3 of 3, guess what happens? These just become a value of 1. Those simplify and become 1. So it becomes 1 times x. Mathematically, this is going to be called the power property that this will multiply. What is 1 times x? And so that becomes x. X equals log base 3 of 9. Check out what do we have right here. Did we have the same thing? Yeah. And then what did I tell you that value is the same thing as? 2. What that means is 3 to the second power is 9. Okay, and that would be your answer. That's the true algebra. So I'm showing you the algebra. I'm going to do the algebra on the left each time, and I'll do the shortcut on the right. Just because on the right I might not have as much room. So that's what I'm going to do each time. So let's do it again here. Go around the world. I'm going to call it that right there. We went around the world. How could I rewrite this one? You tell me how it would start. You write the word log first because it's exponential. Exponential just means the x is the exponent. Okay, now what? 10. We start with the base. Good. So if you're going around the world, what happens next? Y. So with logs, the base is down low, and then the y, the power that's raised to, is in line with the word log. That's how they do it. Equals x. Okay, this one you could rewrite. How could I rewrite this one? Log y, good. It would be written as log y. Oh, here's that swoopy L I was talking about. I'm going to write my L's like this so you can tell it's not an I. I'm going to use a swoopy L. So you would just say log y equals x. Okay, now I'm going to do the true algebra. So if I was doing the true algebra, you come to the problem, you say, oh, my x is an exponent. I want to solve for x. What's the opposite of an exponential? A log. So you would do a log on both sides. You would apply a log on both sides. What base should we pick? 10, because my base here is 10. So you do a base 10 of each side. Still tracking? Okay, so I'm doing a log base 10. Now you fill in each part on each side. This was 10 to the x. This one was a y. Now, what's going to happen with log 10 of 10? That's going to cancel out, and it's going to become the number 1. And this, you're going to learn, it's called the power property. These two multiply. What's 1 times x? And so it's x equals log 10 of y, which you could rewrite as log y. There's your answer. That's the true algebra. That right there is how you would do it using true algebra without a shortcut. But around the world, there's a shortcut for those who want to use it. Okay, I think I have 2 more. Am I right when I say I have 2 more before we move on? Let me check. Yep, part C. Now we're doing no numbers just to try to check it up, just to make sure you're following the process. Go around the world. Okay, this time rather than me telling you, how about you tell me? Log, good. Perfect. R is the base, gets raised to the W inside the logarithm, and that will equal the T. Perfect. Showing perfect algebra. If you said this is exponential, a variable is in the exponent. What's the opposite of exponential? Log, and you take a log of both sides. You get to choose the base. In this case, what's the smartest value to choose to be your base? R, and the reason you do that is because it makes the R's cancel. T, and this one's a W. That's why I chose R. Well, we're going to learn you can actually choose any number you want, but if you choose the number of the base, they'll cancel, and so that's the smartest one to choose. What happens with log R of R? Cancel, and canceling in a logarithm means it becomes a 1, and so it becomes 1 times T. That's going to be a mathematical rule. What's 1 times T? So T equals log base R of W. There it is. So perfect algebra on the left, going around the world on the right. Again, if you understand that shortcut, that's fine. Just use that. But in case that's not working for you, that's the algebra. Let's do it one more time, and then I think I'm done with my examples, and you'll have your first, I believe, DOL. We'll check it out if I'm right or wrong on that. Where do we start? Log. I hear Y. It's the first thing y'all said that's not been correct today. Don't start with a Y. E. We start with E. Why E? It has the power. That means this must be the base. So if I start with E and I'm going around the world this time, which way do I go? I don't know if you remember me saying this. You can go around the world either direction. So where do I go from the E? To the Y. Good. So it's log E Y. When you come back across, that's when you get the equal sign. Equals 3x. What's the first thing we could do from here? Close. He said log y. That would mean log base 10 of y. ln y. Why ln? Let me just make sure everything's in line. Okay, I stick with the same color last time. Let me just stick with the same color. So log base e of y is the same thing as a natural log. And again, it's going to be weird for y'all to get used to this. It's just because natural log, it was invented by a Latin-speaking individual, and they use the word log before the word natural. And that's why it's ln. We just have to get used to that in English speakers. If it's easier to think of it as a log natural ln, log natural. That equals 3x. Okay, this particular problem, we have one more step we could do. What's our last step we could do this time? to get x isolated, I should say. Divide by 3. I agree. So you could actually, the final answer here will be log natural y divided by 3 equals x. Remember, when you divide everything. So the natural log needs to be divided like that. Okay, I'm going to do it again, this time perfect algebra. On the left, I would take a log of both sides. You get to pick the base. What's the smartest pick of a base on this problem? E, because that will cancel this E. Okay. These two simplify with each other, and what do they become? 1. So it's 1 times 3x. What is 1 times 3x? 3x. And what's another way of writing log base E of y? ln log natural y. And then once again, we have one step left. What's our last step? Divide by 3, because those are multiplying. We would divide everything. Whenever you multiply or divide, you either distribute or divide by everything. And I'll rewrite the order here as x equals the natural log natural of y divided by 3. There's your answer. That's the process. That's how you apply the opposite. There's a shortcut, and I'm gonna call that GATW. GATWoo. I don't know. Not much of a saying there, but go around the world. GATWoo, all right? We now, well, I think froze on me. Yes. We now have our first DOL. I have you to try these two. Okay? DOL number 1. Okay, on this first one, I wanted to show you how to, on the calculator, to get to a logarithm. Now, some of y'all already did this here, but just to make sure, if you're going to do a logarithm in the calculator, you press Control and then 10 to the power of x. You see the word up above it says log. If you do that, that's how you can type in that right there. Make sense? One more thing I'm going to show you in case you're at home without my calculator. If you were on Desmos, what you would type in, are y'all watching my screen? If you were on Desmos and you should open up, you type in log. Computer's going really slow. I'm on OG. There it is. And once you type the log, I'm going to do shift and then the minus, and it makes that, you know, that little symbol right there. If you do that on Desmos, it'll move you down low and you can type in the base. So it's log. You hold down the shift and you press the minus, and that's all you do in it. And it makes you the little base on Desmos. Or you can do the functions and find it. But log, shift, minus. If you type in log, it'll do a log, a common log. This is a good review. When I say common log, what does that mean the base is? 10, good. If you just type in log, it'll do a common log base of 10. If you type in ln, it'll do a natural log natural. If you type in log shift minus, then you can change the base to whatever you want it to be. Okay? This is for Desmos. Let me put that on there. That's all you have to do. Okay. Let's pick up. Now, here we go. Convert the following equations from logarithmic form to exponential form and simplify. So again, we're going to have the GATWoo form. What do I mean by GATWoo? Go around the world. Yeah. We'll have the GATWoo form, and then I'll also have the perfect algebra. So where do you always begin? Well, first you need to identify what type of function is it. What type of function is this one? It's not exponential. No. It's logarithmic. So which means we need the opposite or the inverse of a logarithm is exponential. You always begin with your base. That's what I started to say a moment ago, then I stopped. Which one's my base? 7. So you're going to go around the world. And remember, the equal sign is always on the way back. So this one you would begin with 7. 7 raised to the power of 9 equals x. And that in the calculator is going to be some large value. Okay, so that one in the calculator, it's 7 raised to the power of 9. Hit enter. What do you get? Goodness gracious. Let's see here. That would be thousands. This is millions. 40,353,607. 40 million. Goodness gracious. 40,353. Was that the number? 1,000. And then what were the last two? 607. 607 equals x. Okay, perfect algebra time. What you do is you'd say, what's the opposite of a logarithm? What's the inverse operation of a logarithm? Exponential. And how you would do this is you would take your base on both sides, and then the values that were already given become the powers. So on the right side it'll be easiest, it'll just be a 9. The power on this side becomes a log 7 of x. Okay, take your guess now. Guess time. What's going to happen? What's going to happen when you have a 7 raised to a power of log 7? What do you think is going to happen with that section? Just take your guess. They cancel out. It specifically becomes what value? A 0? No, a 1. And it becomes 1 times x. That's what's going to happen. So that 1 times x is x. So you have x equals 7 to the power of 9, which we just solved for as 40,353,607. And that would be our answer using perfect algebra. Make sense? Okay, let's try again. Shortcut, GATWO. Oh, I'm saying GATWO. What does that stand for?
Go around the world.
Go around the world. Where do I begin? 3. I'm beginning with the base. So going around the world, where do I point first? When you go around the world, the world, I guess, would represent the equal sign. You always go across the equal sign. So it'd be 3 to the power of x. You write the equal sign on the way back. 3 to the power of x equals y. I don't think I can simplify that. Okay, so I'll just leave it like that. So using perfect algebra, what is the opposite of a logarithm? Exponential. I would choose the base of 3. So both sides are 3. It's 3 raised to each side of the equation, basically. What I'm showing you is perfect algebra. And on the AP questions, I'll show you why I'm showing you perfect algebra when we take a look at those. Okay, what can I simplify from here? 3 raised to the power of log 3. What does that become?
1.
That becomes a 1. And again, you're just going to learn those will multiply. And so 3dx equals 1 times y. What is 1 times y? Y. It's a good thing I reviewed that earlier. I'm sure you would have been very confused on that. Okay, bad sarcasm. I'll see that one again. All right. But yeah, those multiply right there. That's what happens. Those multiply. All right, we got 2 more, and then we'll take a look at a DOL. These 2 I intentionally did just to make sure you remember your rules. This just says log y equals 2. Is y the base? No. What's our base here? 10. This is called, do you remember what the name of this is? If it just says log and then y?
Yeah.
Common log. This one's a common log. So I'm going to write the word base when I do, I wrote, goodness, I said I'm going to write the word base. I did not write the word base. I put in a base of 10. I'm going to do that for our GATWO here. Am I going around the world? Where do I begin? Base of 10. Where does 10, what does 10 get? Power of 2. And then gets the equal sign coming back around the world is going to equal y. Does anybody happen to know what 10 squared is?
100.
100. We could say that 100 equals y. Very good. Okay, over here using perfect algebra. You have a common log. What should we raise both sides of the equation to? 10. Mathematically, could you pick any number? Yes, but they would not simplify. I'm not going to write that 10 down. I'm just going to write it as log y. What happens with a 10 raised to a common log? These cancel. that just becomes a 1. So it's 1 times y, which is y, and y would equal 10 squared. We already said 10 squared is 100. All right, last one here. Doing the shortcut, Gatwoo. We put a period after the W too. Go around the world. Okay, where do I begin?
10.
E. I hear 10. I hear 10. I hear E. Which one's right? Which one's wrong? One's right. One's wrong. E is right because ln stands for log natural. The log natural, the natural log, is a base of E. So as I go around the world, E gets raised to the power of 4, and that will equal C, because you always get the equal on the way back. So it's E to the 4th equals C. That's one you can type in the calculator. Let's go do that. E to the 4th equals C. We're going to go to the calculator. There's E to the power of X. Make sure you use this one on the far left, that E, not the one at the bottom of the keyboard that's capitalized. E to the power of 4. How many decimals do we need? We need 3. You don't need to round. You can truncate, but you need 3 decimals. And so those 3 decimals will be what I need for my answer here. So 54.598. Since I'm truncating or rounding, whichever one you want to call it, I'm going to say squiggly equals C. That's how I'm going to do that. Because it's not 100%. That would be a rounded version or approximation. Okay, now over here, perfect algebra. If I was using perfect algebra, which base would I choose for each side of the equation to be raised from? Yeah, E to the natural log of C. E to the log natural C equals E to the 4th power. What do I do with an E and a natural log? Back to back like that? Cancel. And by cancel, do you mean make it a 0? Make it a 1. It becomes 1 times C. 1 times C is, that's a 1 times C is what it becomes. Just is going to equal C. C is equal to E to the 4th. And like the calculator said, that would be approximately 54.598. All right. Today we have 3 questions. Time to do number 2. Go to the back of your packet, try number 2. All right, when a calculator is not available, oftentimes a logarithmic expression is easier to calculate by using its equivalent exponential form. Evaluate the following expressions without a calculator. And so I'm going to show you an algebra way of doing this. It's basically what I'm saying. Let's say we wanted to evaluate log 2 of 8. Well, a lot of you, because the logs are brand new, you're not going to know necessarily right off the top of your head what log 2 of 8 is. But you might not know what log 2 of 8 is just off the top of your head. So what you can do, and in this case, if you're evaluating, I'm going to just say this equals x for a moment. Now, was this x actually in the problem? No, so I'm not going to include it in my answer because it's not a part of the problem. I just added it. What I'm going to do is I'm going to rewrite this in exponential form. So I'll use the shortcut. What's the shortcut called again? Yeah, we're going to GAT-W this. GAT-woo it. Okay, if I GAT-wooed this, how will I rewrite it? Where do I begin? 2 raised to the power of x. That would equal 8. The first thing I'm going to do is rewrite it because a lot of you, from this viewpoint, you've seen exponentials enough in your life that you might know the answer. Do you know what power of 2 it takes to get to 8? 3. It is going to be 3. Now, from here, what you can do if you don't know is you take the larger number and you divide into it using the smaller number. But I'm going to use a different type of division called upside down division. I'm going to use upside down division. And I'm going to show you how this works. This is how we're going to get the answer here. So on upside down division, you take the larger number, which is 8, and you're going to divide it, and notice my division, you see how it's upside down? By the smaller number, 2. 2 goes into 4, 2 goes into 8, how many times? 4. Put the 4 underneath. Now the reason I do it upside down is because usually we have stuff written above, but you have blank space down below, and so you have more room to work. Well, what you do once you get your answer is you divide the new answer by the same small base. How many times can 2 go into 4? 2. And you just keep dividing these by the smallest prime number you can until you get the same value all the way down your divisions. You see how it's a 2 and a 2 and a 2? You see that? Okay, so mathematically, how does this tell me my answer? Well, this is saying 8 can be divided into by 2 times 2 times 2, because division and multiplication are opposites. This is telling us that 8 is equivalent to 2 times 2 times 2. Stated otherwise, this is telling us that 2 cubed equals 8. Does that make sense on how that works? And so from here, we can now say, oh, x is 3. Now, did x actually come from this problem? Did my problem have a... No, so I'm not going to include an x. What I am going to do, though, for perfect math, and this is AP, I need to teach you perfect math, is I'm going to go back to the start and say log 2 of 8, and I'm going to say that equals 3. And that would be my answer. So I did not put x equals because I made up the x just to help me solve the problem. I did it just so I could do it around the world. I could do a GATWO. Make sense? Okay, let's try part B. Again, do any of y'all know what log base 5 of 3,125 is off the top of your head? No. So what's the easier way of solving this? Easier way of evaluating without a calculator a logarithm. Let me rephrase. GATWO. Let's go around the world. Let's do a GATWO to get it to... Let's get it to exponential. All right. Kalaya, walk me through it. Where would I start? She says add an equals x. I agree with her. So if I'm going around the world, where do I begin in the expression? Start at the 5. 5 to the power of x equals, perfect, 3,125. Now that we have it in this stage, it's easier to figure out the proper way of lining it up. I'm going to do upside down division just because we have more space going down than up. That's why I do it upside down. There's no special reason for going down other than you have more white space. That's the only reason I do upside down. So which one's the smaller number? 5. So that one's going to divide into the larger number. 3,125. I will show you problems where the base happens to be the larger number as we go forward. It'll work the same way. And I'll show you when we get there. Okay, start with this, with division. Can 5 go into 3? So then you ask, can 5 go into 31? It goes in 6 times with the remainder of 1. I want to put that there. So now you ask, can 5 go into 12? Yes, it can twice. So I put a 2 there, and it has a remainder of 2. So I put the 2 up there. Now you ask, can 5 go into 25? 5 times. And so this tells us that 5 goes into 30,125, 625 times. Now what do? Do I stop here? Go again. Dividing it again, 5. Can 5 go into 625? Answer is yes. 5 goes into 6 how many times? Once with a remainder of 1. Put that there. Okay. Can 5 go into 12? Twice with a remainder of 2. Can 5 go into 25? 5 times. Are we done? No, because we did not arrive at 5 yet. We're getting closer. So we do it again. Thomas, can 5 go into 125? Yeah, let's see how many times. Can 5 go into 1? And we'll get there. Can 5 go into the 1? Can 5 go into 12? How many times? 2 times with the remainder of 2. Put the remainder up on the next number. Can 5 go into 25? How many times? 5 times. All right, we are so close to being done. Are we done though? No. Can 5 go into 25? 5 times. Now you are done. Don't do it another 5 where you end up with a 1 because students just get confused. Just stop there because I'm all 5s. Now, how many 5s do you count there? 5. Now, we were dividing, which means the opposite of division is multiplying. That means if I multiplied this 5 times this 5 times this 5 times this 5 times this 5, you know what I would get as a product? 3,125. Because of that, you could say that 5 to the power of, let's see, 1, 2, 3, 4, and 5. There's 5 5s. 5 to the power of 5 equals 30,125. Make sense? Now, did this problem start with an X? So to be perfect in our math, and again, this is AP, so I want to try to be as diligent to be perfect as possible. You would not say X equals, you would say log 5, 3,125 equals 5. And that is a true answer. You can check it in the calculator. Do y'all want to check it or you trust our math? Think we did good math? You want to just try it? Let's just try it. Again, to do a log, log is on the left side. You do a control 10 to the power x. And again, on Desmos, just do log shift minus. What was our base? 5, and the number inside the log. And by the way, it's this value that must be positive. When I was telling you that logs have a domain of only positive numbers, this value must be positive. Answer's 5. We got it right. Good work. All right. We got a few more, and this is one. Now I'm going to show you how there's times where you don't get a perfect answer, and I'm going to show you what happens there, okay? So let's walk through our process. What should we do first? Let's add an x to help us evaluate. Does anybody know what log base 4 of 32 is?
No.
4 is an answer. We're guessing. It's not going to be right because 4 times 4 is 16 times another 4 is 64 times another 4 I think is 216. So it's way too big. But it's a good guess to start us off. Do we know what it is though? No. So what's the easiest way to solve? Let's get woo it. Go around the world. All right. So where do I begin with our going around the world? 4 raised to the power of x is going to equal 32. Now, once you have it set up this way, it's easier to see. The whole purpose of going around the world is just to help you see easier the setup. Okay, now choose a larger number first. Which one's larger?
32.
32. And 32 is going to get divided by 4. Can 4 go into 32? Can 4 go into 32?
8 times.
Yeah, 8 times. That's correct. It is 8 times. 4 goes into 32 8 times. All right, now you ask yourself, can 4 go into 8? Whoops. 4 goes into 8 twice. Uh-oh, we have a problem. They're not all the same numbers. This is saying 4 times 4 times 2 is 32, which is great. That's a math truth. 4 times 4 times 2 is 32. However, I cannot say this is 4 to the power of 3 because that is not a 4 right there. Do you see my problem? So here's what you do now. We have found that 4, this is not going to be an integer value. It's not going to be 4 to some whole number. What it is going to be, though, is 2, because 2 is a smaller number, 2 to some power. So now I come back and I say, all right, I realize I need my base. We need to change the base to 2. That's the idea here. Change the base to 2. Now, you remember how we had that property with exponentials to change the base? That's basically what we're doing here, but doing it on upside down division. It's a little bit easier to do it here. So I'm going to change the base to 2. So I'm going to go back to these 4s. Can 2 go into this 4? How many times? 2. Okay, can 2 go into this 4? 2 times. All right, you know what we just discovered? We just discovered 2 things. That 2 to what power, excuse me, 4 is equal to 2 to what power? 2 squared. We just discovered that 2 squared is equal to 4. Make sense? Because any 4, it took 2 2's. We got that? We also discovered 32. How many powers of 2 is equal to 32? Count up the 2's. How many 2's do you see there? 1, 2, 3, 4, 5. I'm seeing 5. So 2 to the 5th power is 32. We all following that? All right. So I'm going to come back over here. And now that I know that this is true, what I'm going to say is 2 to the power of 2x, because this is power to a power property from exponentials. So instead of 4, you see how I changed the 4 to 2 squared with the x, because it had an x, is going to equal, what's 32 the same thing as? 2 to the 5th power. Make sense? So I took these 2 values, and I'm going back up here with it. This is called, right here, that was the power property that we learned before, and that's just straight substitution, 32 becoming 2 to the 5th. Now I'm going to do a new property that I haven't showed you, and that's called the 1-to-1 property. 1-to-1 property, and it means this. If you have the same base on both sides, you can cancel out the base. And so if 2 to the power of 2x equals 2 to the power of 5, that means that 2x equals 5. What happened to my bases of 2's? They cancel each other out. It's basically like you took a log 2 on both sides. They just cancel out. So 2x equals 5. So we're one algebra step away. How do I get x isolated? What's the opposite of multiplying by 2? Divide by 2. And so what do we get for our final answer? 5/2. Oh, I shouldn't have wrote an x though,
Okay,
because we made up the x. So I'm going to rewrite it as log base 4 of 32. Now I'm going to give you a shortcut here. So just make sure you have that in your notes, and I'm going to give you the shortcut. Are y'all ready for the shortcut? Not going too fast? Here's the shortcut. Next time we do the upside down division, we realize the numbers that 4 isn't a good number. I have to change the base. Once you find your values that 4 is 2 squared and 32 is 2 to the 5th, once you get that spot, you can look back at the original. The base, the lower value, you see how the base is lower than the 32? That's your denominator. 32 is going to be your numerator because it's a little bit higher. So 2 went into 32 how many times? 5, that became the numerator. 2, it was 2 to the 5th power, gave us 32. The 4, that's down here a little bit lower, let me point at it. So the 32, since it's a little bit higher than the 4, gets the 5, which it's in the numerator. 2 went into 4 how many times? Twice. Because that's a little bit lower. That's going to become the denominator. That's how it'll always work. So that's a shortcut of getting to 5/2. So once you did this part right here, you actually have everything you need for your answer. It's just the 32 is going to get traded to become substituted to a 5 in the final answer. And the 4, when you get rid of the logarithm and all that, that'll be substituted to become a 2. Make sense? A little bit, maybe? All right, I have one more. This one's actually going to be quite a bit easier. This says log 1000. I want to change the phrasing of it. I should say common log. Why should I say common log? Do you see a base? What's it mean the base is? 10. This means it's a 10. To help us evaluate this, I'm going to put it equals x. Does anybody know what the answer is off the top of your head? 0? No. Okay, since we don't know, let's go around the world with it. Karen, what should I do to go around the world? 1,000? Okay. Answer's not 2. It's going to be 3. How do we get 3? Well, I'm going to do upside down division. I'll do upside down division here. We got it rewritten. I'm going to take 1,000 and divide that by 10. 10 can go into 1,000 how many times? Well, how about this? 10 goes into this. It does not go into 1, but 10 can go into 10. 10 goes into 10 how many times? 1 has no remainder, so I don't have to put a value. 10 goes into 0 0 times, and 10 goes into this 0 0 times. We're not done. We don't have the same base, so I divide it again. 10 goes into 100. Let's see. 10 goes into 10 how many times? Nope. 10 goes into 10 once. Now 10 goes into 0. I got you. You were saying that value. Okay. Do I have the same base all the way across? This one's easy. Don't have to change the base. This is saying 10 times 10 times 10 is equal to 1,000. Another way of rewriting that is that 10 cubed equals 1,000. If 10 cubed equals 1,000, now we can write our answer here. I'm going to write it as a common log. I'm just going to say log 1,000 equals 3. Log 1,000 equals 3. I wrote it as a common log. I did not write the 10 in. I did not write the x. That x is not a part of the problem. 10 you don't have to write there. Just a common log. All right. You've seen a number of these now without a calculator. What? I forgot I had these. All right. Last little things I got to show you. Some weird ones. Log 16 of 4. Anybody know the answer off the top of their head or want to take a guess? -2. It's a great guess. Let's see. How do you solve it without a calculator? Since that's what we're doing. Without. Nope. Well, how about let's get woo it first. Since we're not as familiar with logarithms, let's change it to exponential, and it's just easier to make sure we get the right answer. If we're gat-wooing it, how would I rewrite this? To the power of x equals 4. Great. That's going around the world. Now from here, you pick the smaller number to divide into the larger number. What's our smaller number? 4. 4 is going to divide into upside down into the 16. And the only reason I say upside down is not because you have to do it upside down. It's just because you got more white space going down than up. 4 can go into 16 perfectly. How many times? 4. Can I stop there? Yes, this is telling us that 4 times 4 is 16. Say it another way. 4 squared is 16. Okay, so now I'm going to substitute this. I'm going to say since 4 squared equals 16, I'm going to take this value right here, and instead of 16, what are we substituting in? 4 squared. And because this has 16 to the power of x, it's 4 squared with an x. That's the power property, power to a power, you can multiply. So 4 to the 2x equals 4. Now, I have the same base on both sides. Because this 16 had an x right there. Okay. So it's 4 to the 2x equals 4. This does not have a power. What's its power? 1. What I'm going to do now is called the one-to-one property. And it just means this. If you have the same base on both sides, 4 raised to the 2x, 4 raised to the first, you can cancel out the bases. And what are we left with? 2x equals 1. By the way, if you did not want to do one-to-one property, another way of saying it is I could say I'm going to take the log of 4 on both sides. That would be doing the opposite. If I took the log 4 on both sides, this would cancel, this would cancel, and I'd be left with 2x and 1. So it's the same thing. All right, we got one step left here. What's the 2 doing to the x? It's multiplying. So to solve for x, you got to do the opposites. You got to know your inverse. What's the inverse operation of a multiplication? We divide both sides by 2, and we find out that the value of x is 1/2. Oh, I shouldn't write an x, sorry. What should I write instead of an x? because those were equal to one another. We added the x. That was not part of the original problem. So perfect math, you would not say x. You would say log base 16 of 4 is 1/2. Go ahead. All right, last one here. Last, I'll call it a weird one here. Anybody have any ideas what log 3 1 is?
What?
1/3. Great guess, but no.
Uh,
Well, let's go. Let's get woo it and find out. I'm gonna add the x. Ooh, might have just heard the answer. Okay, if I go around the world, it becomes 3 to the power of x equals 1. Now this one, I don't know really how to show you upside down division. I have no way of showing you upside down division. I could try to do it. You would say, what's the smaller number? 1. And you would say, how many times can 1 go into 3? And how many times does 1 go into 3? 3 times. And then you'd say, okay, how many times can 1 go into this 3? Okay, and you see my dilemma here? Whoops. This is like an infinite, to quote Buzz Lightyear, that's going to be to infinity and beyond. It's just going to go on and on and on and on. We have a problem there. You see that? Different rule. Do you remember in exponentials? There's a power that always makes the answer become a 0. Darn it, said the answer. There's a power that makes the value always turn to a 1, no matter what the base is. No matter what the base is. What's that number? 0. Anything to the power of 0, this infinite loop is only solved. Anything to the power of 0 is equal to 1. Here's the reason why, if you want to know, is because think of it this way. If you use your exponential rules, if you had 3 to the first divided by 3 to the first, 3 to the first divided by 3 to the first. Well, let's just talk. What is 3 divided by 3? Because that's ultimately what I'm doing here. My answer will end up being 1. But by exponential rules, if you have the same base being divided, what you can do is subtract your powers. You remember that rule? That was called the quotient property. Remember that rule? And what is 1 minus 1? And that's why anything to the base of 0 is always equal to 1, because you could rewrite it, base of 0, as power 1 minus 1, which would be the same thing as 3 to the first divided by 3 to the first, which we all know that is 1. So that's the rule. This value up here, we're going to get the answer 0. Log base 3 of 1 equals 0. And that's since anything raised to the power of 0 is 1. Since any base raised to the power of 0 equals 1. That's the reason why. That's a mathematical rule. Any base raised to the power of 0 equals 1. And since that's what we have here, 3 raised to some base equals 1. The sum base must be a 0. All right, you saw me do 6 there without a calculator. I want you to try number 3 in the back of the packet. Go try deal number 3. All right, example 4. Now, the example 4, all it is showing us how to use our calculator. We've already done this, so I'm going to go fast. How do I do a log 2 of 10? Log base 2 of 10, I should say. Control what? 10 to the power of x. Whoops. Base of 2. 10 here. I'm getting 3.321 approximately. And then the last one was just a log, and I'm going to leave the base blank just like they do. Log of 9. So I'm going to leave the base blank. What does that mean the base is if it just says log? 10. When I press enter, it'll fill in the 10. But these would be my answers here. You would just take 3 decimals. You don't have to round. If it says round, then I technically would. You don't have to round though. In AP, you can just truncate. Okay, but I'll go ahead since it says round, I will. You don't ever get counted off for rounding, but if you truncate, you get the correct answer as well. So 3, 2, I'll round this one since it says 2. 3, 2, 2 approximately. And then the second one is approximately, I do a squiggly again, 0.954. That's how you would use a calculator. Okay. So now let's try DOL 1 on the back. All right, to finish up this lesson, let's talk about what we call a semi-log plot. Semi-log plot. One of the things that can happen in mathematics is when we look at an exponential graph. Remember, an exponential graph either looks like an airplane taking off or an airplane landing, or if it's below the x-axis, a submarine coming up or a submarine diving down into the water. Whenever we're dealing with exponentials, because the graph grows at such a fast rate, you can get lost on the y values of finding out like what's the difference here, like what are the exact y values. This goes from 0 to 1,000,000. Now over here it's easy to figure out, okay, this is approximately 7 million, this is like around a little over 5, between 5 and 6, but over here it's very hard to tell the difference in these points. Like, is this 0 people, is this 10 people, is this a 1,000 people? It's so hard to tell. So the problem with this is this exponentials grow so quickly. Now, this is a normal y-axis. What we're going to do is that if you have an exponential function, we're going to take what's called a logarithmically scaled y-axis. And that just means we're going to take the log of both sides of the equation. And while we do that, we're also going to take the log of the y-axis. Now, what will happen is the data will appear much more linear, and it'll be much easier to find what these values represent. These data points are the same as these data points. The difference is I've taken a log of the y value. So whatever the y value is, we take a log of it. And so that's what these values are. Here, 10 to the first, that's this 1 here. Notice, I mean, you could type these in. 10 to the 7th would be 7 million. 10 to the first, though, is 10. So instead of going from 1 million to 7 million here, or 0 to 7 million, counting by millions, now I'm counting. What I'm doing is I'm counting by powers. So this is 1 power, 2 power, 3 powers, 4 powers, 5 powers, 6 powers, 7 powers. But the difference is this is going from 0 to 10. This is going from 10 to 100. This will be from 100 to 1,000, 1,000 to 10,000, 10,000 to 100,000, 100,000 to a million. And then the 7 zeros, that's actually more than 7. I said 7 million. That's not 7 million. That's actually 10 million right there. So that's what's happening is you're adding a 0 to the number every time. Notice the data is much easier to distinguish points. And so that's called a logarithmically scaled axis. Okay, so mathematically, how does it happen? It says here, the population data of English Americans in the United States since 1620 is shown above. The population data for the years 1840, 1860, and 1880 are given below. Plot these 3 additional data points on the graph above. So in 1840, there was approximately 17 million people. And so since 1920, so 1840 is 120 years. Here, 1820 is the same thing as, let me write it over here. This is equal to 1620 plus 140. So the x value here, or the t, we are going to say this is 100, I can't do math, plus 120. This is going to be 120. This is going to be a t value of 140 because this is equal to 1620 plus 140. And then this one right here would be 1620 plus 160. And so this will be a t value 160. So what I would do is I would go 120 and then 17 million. So I go to 120 here. And from 120, I need to find 17 million. So I'm going to come up from here somewhere. And again, this is 10,000. I still can't do math. That is 220. These are all 200s. My goodness, what is wrong with me? These would be 200s all the way across. Terrible math. Okay, So 1840 is 1620 plus 220. This will be plus 240. And this is plus 260. Okay, so let me move this over. At 220 years, which is equivalent to 1840, we should be up at 17 million. So again, this is 1 million. This is the same thing as 1 million. That's a 1 followed by 6 zeros. This right here would be 10 million. So if I went to the next line here, this would be 10 to the 8th, which would be 100 million. And so if that's 10 million, this is 100 million, 17 million is somewhere in this line. And so I would come from, let's just say over in here somewhere, and I would look for where these two values intersect. And that's where I would put that data point. I'll do that one in blue. Okay, that would represent the value 220, comma, 17 million, whatever it was, 17,069. Come on, 17 million. I've already forgotten the number now. 069,453. 069,453. I did not put the commas because I thought it would get confusing. Now, for at 240, we need to add the point 31 million. So let me come here. At 240, we need to add 31 million, which is going to be somewhere higher. And that would be that point right here. This is 240, 31 million, 443, 321 maybe, 321. And then finally, the last one, we would have at 260. And the number would be, let's see here, 50 million. So 260 and then 50 million, whatever. 50 million, 189,289. 189,209, I think. And those would be your three data points. So even though it's exponential, now it's kind of looking more like a line. So that's what happens when you take a semi-log plot, is it'll make exponential data look linear. Okay, so here's the DOLs, and again, I'm showing you this now with extra marks to make this easier. These from 10, I want you to know this says 1 down here. It doesn't say 0. Usually we would have the 0, but that's because 10 to the power of 0. You're counting by your powers. Remember, on a log scaled axis, you count by power. So 10 to the 0 equals 1. This would be 10 to the first equals 10. This would be 10 squared. This would be 10 to the third power. Notice you're counting by powers, 0, 1, 2, 3. Now within those values, you're counting by when you reduce it, that's a 1. So this means this is 2, 3, 4, 5, 6, 7, 8, 9, 10. See, 10. Now I'm counting by tens. So this is 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Now that I'm here, I'm counting by 100s. 100, 200, 300, 400, 500, 600, 700, 800, 900, 1,000. And that's how it works. So I'll let you plot these 5 points on this graph here. All right, now go to AP Classroom and try your 3 questions there. Lesson 2.9. Get those submitted and turn them in.